Hi, this is Sheldon Cohen, welcoming you back to the afternoon session for the AADL and ACVIP User Day. We have three presentations this afternoon, all from organizations that participated in the MSAD Mission System Architecture Demonstration Project with the Army. Our first speaker up today is Dr. Jason Duran, who was with the Northrop Grumman organization in San Diego. His talk will focus on SysML to ADL using the object constraint language. Jason, please start off.
All right, thank you. So just a real quick outline, we're going to talk a little bit about some of the items and concepts that are necessary to get some of the transforms in place. And then we're going to step through a couple of examples for the power, latency, resource, weight, and then also talk about some common issues that occur. Hopefully you can see my my screen here. That all going? All right. Just to start with, these same sorts of techniques can be used to transform, to do cyber physical analysis, which is really what we're talking about today. But the same sorts of techniques you can use to transform to output like ASIM. So if you're interested in mission simulation or R statistical files and AI to do other types of analysis. So some of the building blocks that we start with is really is understanding what it is we want to get out of the model. These are the different kinds of analysis that you might want to do: reliability models, electrical models, logical structures. You really have to understand what it is you're going to use the model, any model, be it a SysML model, et cetera, before you start and undertake that endeavor. That way you get value out of what you do. And so what you see here is just the standard building blocks really for the different system context, system form, some initial MOSA aligned integration analyses that we want to get out of the model. So, and then what we do is we construct that over on the right in what we call a domain of discourse, which is really just a meta model where we're going to document how we're going to link all these different concepts later on. And that's important, especially when you want to start using OCL later on, so we can check that these relationships exist or not. And then using those same sorts of things, if we're gonna do an electrical diagram, certain things or electrical analysis, certain things have to be there. And really what we're trying to do is we're trying to ensure these relationships are correct, that values in the model are filled out correctly, so that when we do execute a transform, it has all the necessary components to run that analysis. If I transform this into AADL, I want to make sure that the OSATE tool can actually do those kinds of analysis. Or if there's an error, especially because this might be an automated process, and that error might occur in a log somewhere, you have to track it down to figure out why it failed. You really want to do that ahead of time. And that allows some of the other engineers who might only know SysML to ensure that they model the system correctly and that all the proper information is there to do the analysis. They might not even be aware of how that's conducted using AADL, but they certainly have all those properties and they can enter that information. And so that's kind of some of the starting concepts. Using the OCL, we use the OCL to enforce, again, the relationships, where that content goes in our structure, so that we can help to identify duplication or that different concepts may have been represented multiple times. And then, as you see down on the bottom, we can also do validation. Where we're going to do queries. We're going to use some of these OCL queries to check for content that might be missing or content that might be not correct, et cetera, to do the transform. And so that's kind of what we're going to use, and we'll talk a little bit more about that. Some of the other things to bear in mind is that you want logically equivalent models, so that whatever you have at your logical architecture, you want it to mirror that design level. And it's important that you start somewhere. You have to start the analysis somewhere, but you want it to reflect. And you may not want to share all the details of the design later on, but I still want to be able to share to meet a lot of these objectives and to allow people to perform the same sorts of analyses, at least in terms of resource loading, other things that might have been enabled. And so you kind of have to understand the relationship and then be able to map the values back and forth. Again, with a robust set of rules, I can use scripts about how these things relate. And so what you're seeing here is the design and the logical levels. I can ensure that the values stay synchronized within my model because I know there's supposed to be a relationship. I can check for that relationship with the AADL. And kind of what you see here is some of the transforms down below with the AADL output. Now we've been using the CAMET tool set, so that bridge that we talked about earlier. Everything that you see today was done using the 1.5 version. There's a new, it's all the way up to 1.10 now, which we're currently testing, and that works with the 2021. So again, ensuring that you keep those synchronized. You can, again, use the OCL and scripts to ensure the values stay mapped. So that kind of takes us to the first real analysis. And so this is just a very simple power analysis where I have suppliers on the right. I have a backplane that might flow through. It could be a bunch of cabling, so it could be N of these things. And they could flow across different wires, different harnesses, et cetera. And then I have consumers over on the left. Now, that's a SysML representation, but what has to happen is you have to annotate that SysML with some of the stereotypes, as I previously mentioned, that were provided in the CAMET toolset. And so what we're really doing is we're using the OCL to check to make sure that all that annotation is done correctly, so that the rules later on when you transform it, it's going to run. So we prevent that. And kind of what you see here is the output of some of the AADL on the top right. And then when that analysis actually runs, it's going to look at not only do you supply enough power, but is there enough capacity to actually flow it over these things? And so then you want to be able to read those values back in from the results and pull that back in. But in order to do this analysis, you really have to have one, to be able to designate the scope in the model. Two, you have to identify what are the suppliers, the power suppliers, what are the. That so happens that you have to use a lot of the stereotypes anyway, so you can use the OCL to key on, if this is the context, this is a diagram, perhaps I apply a stereotype to identify that diagram, IBD in this case, as the context or as a power analysis. And then from there, the context of that IBD tells you what node, what block you're working with. And from there, you can begin to interrogate using OCL its inner components, and whether or not those properties are filled out, et cetera. And so that's kind of what you see here. In the next example, we have a latency analysis. And this is something we're working with now, especially if you want to understand startup sequence or something like that, as it flows across multiple layers. And really, it's composed of two different kinds of diagrams. You have the data connections like you have up above, and those may be allocated to other layers down below using the allocation and then specific SysML stereotype. And so those can have n levels going as deep as you want, or start as high as you want. In this case, maybe I'm just looking at the computer going to the communication systems, and that's as far as I need to go. But maybe I go 3-4 levels below, all the way down to the processor threads. It's really up to you to determine and document all of that. Now, the flows themselves is really what you see on the bottom is really a set of sequences, and those sequences can call other sequences. So in this case, it's a sequence and a lifeline, and that lifeline is actually stereotyped as a flow, AADL flow, which means that it's another sequence within that sequence. And typically, some of the terminology here is you have a source, a sink, and then an n number of flows in between. So where does it start? Where does it end? And however many sequences it might flow over. And then each of these can call out additional. And really what it is that each of these sequence diagrams spells out the ports that you might see up above that it's traversing at each of those levels. Ultimately, what you end up with is an output, kind of like you see on the right, that details the actual layers that it traversed. And so again, you can write a set of OCL rules to enforce that you selected all your lifelines are ports, the features. They have to be features if you do the ports. So each of those ports has to be tagged as a feature in order for that transform to work correctly. And so you have a set of OCL rules that will tell you if you, in any given sequence diagram, which is so annotated as a analysis, whether or not it achieves all of those elements. And the same is true up above with the data connections. You can understand whether or not you're missing things or things don't flow. Maybe they're left dangling or something. You run into all sorts of things, but ultimately what it is you build out these rules, and these rules get a little bit bigger as you try to transform it. Typically, what we did was we would do the diagrams, and there would be several errors in the system model, or at least incomplete portions. We would execute the transform. The transform would then tell you, once you loaded it into OSATE, here's the errors, here's what's wrong, and then you have to kind of circle back and figure out what additional elements the system model diagram or what additional tag needed. And so really what we then use is the OCL to go find those elements as you execute it. So again, latency. The same thing for the resource loading. You might be looking, again, the binding. Binding, in this case, software and the software to the actual processor and or memory. And you can then, when you get into the OSATE tool, you can then get it to output whether or not you're exceeding the budget, et cetera. So the same sorts of analysis, same sorts of things that you're looking for. Now, that's a visual representation, but you could also just use if you had a list of all your software processes and the hardware, you can also use a matrix to do the allocation in a non-visual way, and that's a little easier to maintain. But that's the visual representation. And the same sorts of analysis can really happen at a weight. In this case, you have an element, let's say a system. In this case, it's the AADL system. You see they get these different icons when they have been tagged with some of the AADL content, so you're aware of what is actually being generated and what's not. So in this case, I have some weights, and those weights would be associated with that system. And again, I can write OCL to understand whether or not the communication system has tags that have been filled out, because it has to have a stereotype, and whether or not, if it matches to one of these data blocks, whether or not the data blocks actually has values in them. So you test at all the different levels, even for something as simple as a weight. In this case, there's a weight limit and a gross weight. But you can do that really in terms of the weight analysis. You can construct these at any given layer. A system might have a total weight limit, but maybe a particular subsystem has a portion of that. So you can begin to do, especially at that logical level, your high-level budgets and budget applications. And then later on, when you have you can use these same tests. What we found is, suppose I have the latency, and I did the budgeting in that latency example. I might have, that might be for the design before I've ever implemented anything. And then later on, you now know the points in your software where you're going to want unit tests to record time values. You can take those time values and essentially load those exact same things as observed values, run the exact same analysis against those observed values, and essentially reuse the test that you have, one against the design, one against the implementation, and then of course record the results of the testing. So that's kind of how we're applying and using a lot of this. So here's an example of reading the results back in. I might have a set of requirements, whatever those may be. I have analysis, doing different kinds of analysis to satisfy different things, whatever those might be. And then the latest status on that requirement as read in, parsed from the results. Again, every one of those SATE produces SATE analyses produces a report. You can parse that report to return the value, or you can put it into a database that's there as well. It's nice to have in a requirements trace matrix to be able to see the status of them, and then also be able to see how that requirement might flow across my design, either functional or non-functional, etc. So that's kind of, again, it's navigating those same relationships that you saw in the domain of discourse to understand how things were tied together, so that you can display those results correctly against the correct items. So I'm gonna change now. So those are basic analyses and kind of how those work. What I'm gonna talk about is a few of the problems that we've seen. So what you see here is straight from the examples that comes with the tool set. So there's a high level mission analysis example that decomposes to a lower level, but some of the properties in some cases, some of those AADL types allow you to put the values into a tag value, and sometimes they actually read the value from the name. And so in this case, you can see there's a part called 500. That's actually the value from where the bridge tool is reading the value. And that means that sometimes it's reading from the name, sometimes it's reading from a tag value somewhere. That makes it a little bit harder to automate. So one of the things that we found is that if we overloaded some of the SEI definitions, we could then basically assign it to its own value and not have to have these, part just for the name of 500. And who knows if I'm going to have a value called 500, is it used one place or another? You don't know the units, you don't know. I can't have more than one 500, but if I did in the model, how would I actually do that? So it presents all kinds of problems. And that's by overloading those tag values in that profile, we can redefine it basically to a tag value and move around that. And so that's one of the things that we've definitely done to get around some of these issues. So this is just something, one other thing to note is that the SEI, the bridge tool from CAMET will port a lot of these values. We also find that the order in which some of these values or units fields are created can appear one before the other. And it really has to do with, and we think that, or at least we suspect that it's based on the actual order that they're created and that they appear. So one of the APIs somewhere is loading those nested values, and they appear in the order that they're created. So we make sure that in order to get this to show correctly later on, you'll see an example, we'll make sure that the data value was created first before we do the units. So it's just another nuance of Cameo sometimes. Some of those APIs, even though you might see it in alphabetical order, you would expect that alphabetical order to still be there. It's not in some cases. So here's an example. where the transform. Now, I mentioned that if we overloaded, we could overload, but the problem here is that the parsing tool doesn't, it kind of outputs something with these extra brackets and this extra notation that you see up above. And you really want, in order to be, for that to be clean, it's got to be what you see on the bottom. And so what we did was just a very simple Python script. We actually, so our order is to do the SysML, execute the transform. Transform puts out these files, and then to run a Python script over those files. And now you can actually use the OCL tool to perform the analysis. Once you perform the analysis, you can read that back into the model and record the results of the analysis, etc. But again, sometimes you see that if I had created the units before I created the rate, you'll see that flipped in the tool. And so just be aware of that, that particular nuance. In this way, we're able to transform, run along that. So this is a continuation of that transforms. So over here, you see that we laid out power analysis example, and I have a series of different checks that I really want to check for. And this is an example of how I can narrow down. Maybe I'm looking for my initial elements. Do I have a budget? Do I have a capacity? Do I have the power? Do I have the supply? Once I have those supplies, I'm going to use refined sets of OCL to actually figure out where the value in units for that is the port direction correct. If this is a supply, it should be, the power should be going out. If the power is going in, you essentially have a node potentially with two ins, and that'll cause an error in OSATE. So you again want to ensure some basic things to know that it's going to work correctly, and then what you see there is just an example of some OCL to actually do some of this check. Really, we're using OCL as a search. Each of these smart packages, these are smart packages in the CAMET or Cameo tool. That allows you to enter in an OCL script, and that OCL script is what you see here. So here's an example of I'm looking at all of the ports. If you saw on that diagram before, there are a lot of ports, but I want to know which ones got the wrong direction, and I don't want to have to click on every one of those ports to find the one that's not right, that's causing the error. In this case, again, I said that it was a supply, so it's a supply, it should be powering out, the direction should be out on a power analysis if that's the supply, given that context. So this is going to find ones that are not out. The very bottom part, and essentially what it does is it returns that actual port object, which means from here in Cameo, I can just double click on the on that particular block and correct it right there. Again, I can pass the same sort of analysis, the same OCL as queries kind of. I can pass this from one program to another. We actually put them in a profile that we make available across all of our different programs, so that we can share that profile with these different things. So if they want to do a power analysis, they can do that. Or at least ensure that they model it correctly to do the AADL analysis. Now, you can also extend. This is just an example of extending those same sorts of relationships. So if I wanted to do mass, I could write OCL rules to ensure that I would take the domain of discourse, I would add this AADL mass. I would say that every one of these types should have, if I have a stereotype of this, it should have at least one or more of these masses. Because you can have a weight limit or an actual weight, or you can have a gross weight and that weight as well. So there could be more, but maybe I want to say that everyone has to have at least filled it out. And I might write rules that Doesn't matter if it's 0 or not, it's got to have a value. So that's also part of the rules, because otherwise it's going to fail in the analysis. But you can write a series of OCLs to then check that all the things all the things that I've designated systems, subsystems, and core components all have weights. And it's just another example of extending that same thing out. And we actually do this with the same sorts of thing with AADL, passive type concepts as well, on different missions, mission context. But the same thing using OCL to understand what those relationships should be, write the rules to make sure that it's enforced. So that's kind of where we're at. It's the conclusion of my presentation here. I might have just a little bit of time for some questions.
Hey, thank you, Jason, for your presentation. We do have a few minutes if there are any questions. I don't have any in the question area, but if anybody would like to direct their questions to Jason at this time, we can do that.
So as somebody who was a panelist earlier, I can cheat the system a little bit and just jump straight to asking a question. Okay. First of all, this is really cool. I'm impressed by this. I apologize if you mentioned it on the last chart. You had a key, a color-coded key. Is that something? Yeah. Is that something you were able to generate and apply with OCL, the color coding, based on stereotypes?
Yeah, so that just comes with from it's a legend, is what it is, and that legend is just in the SysML. So you create your legend item, and essentially you're right. What I'm doing is I'm applying them to the different concepts that are represented. In the very beginning, I said I want to show that I have system context, use, system function, system form. I want to know when those things are separate. I want to know what's logical, what's physical. Also for IP purposes, you want to understand that separation. So it's really just a legend in Cameo, and then with that legend you can apply it to the blocks. Once you apply it to the blocks, it carries forward in all the diagrams, assuming you have that same legend on.
Okay, thank you.
You're welcome.
And we have one other question in the question area.
Yep.
It's asking about the latency example. What AADL stereotypes did you use on your components? That's been very interesting.
Okay, so in that case, you have, let me scroll back up. So in this case, you have the flows. These are essentially sequence diagrams that you're going to tag with that AADL flow. These are just SysML internal block diagrams where you're going to show that data connection on that top level of analysis is what it means to do the traversing through there. Again, you can allocate these to the lower levels. I think in this case, I've also assigned this as an AADL connection, which allows you to put in some of these other properties that you see here. Bandwidth, budget, latency, etc. So there might be, you might assume no latency, you might assume some latency, and then there's bounds too. The analysis itself lets you, there's a minimum and a maximum types of bounds. I definitely recommend starting off simple before you get complex, but you can make it, you can go a bunch of levels to the level that you need. Just keep it simple to begin with. Hopefully that answers your question.
Okay, thanks, Jason.